Hello, family. Welcome to another session of Maths Fanatics 24/7. In this video, we're going to be looking at grade 9 revision on forces. Okay, without wasting any time, let's get to the point. So the first question, they want us to give one term for each of the following descriptions. Here, A, they say an influence that can deform a flexible object or change the motion of an object with mass. Obviously, that is a force, right? That is a force. Let me just get this. So the answer here will be a force. Okay, we can move on now. A region in space where an object with certain properties will experience a force. That is called an electric field. It's called electric field. Perfect. And then when the only force acting on an object is the force due to gravity. So here is like when you have an object falling right from the sky, we call it free fall. No? We call this free fall. For example, when you have a stone, you throw it up. As it comes down, if we neglect the effect of air resistance, the only force that will be acting on the object will be the gravitational force. So we say the object is in free fall. An object that is in free fall is the object with which is only experiencing the force of gravity. Perfect. Then they say the two opposite ends of a magnet. Remember, a magnet is made up of poles. We call them poles, which is the North Pole and the South Pole. So a magnet is made up of the North Pole and the South Pole. Okay, then they say a fundamental property of matter that comes in two types and is carried by protons and electrons. Remember, protons and electrons are charges, right? So here, the fundamental property of matter that they're talking about is the electric charge. Electric charge. The electric charge. Perfect. You can move on now. Okay. So on number 2, they say 4 possible answers are given for each of the following questions. There is only one correct answer. Write the letter on the line below each question. Okay. So which one of the following statement is false? Let's check. In order for a non-moving object to start moving, a net force must act on that object. This is true. For an object to start moving, there must be a force applied that is greater than the frictional force. So there must be a resultant force, of which we're going to talk about it later in this revision pack. Okay. Then B, they say contact forces are strongest when objects experiencing the forces are touching. This is definitely false. No? Remember, contact forces, basically the strength of contact forces is not determined by whether they are touching or not touching, right? For contact forces to exist, whether weak or strong, the objects must be touching. So the strength is not determined by whether they are touching or not. That doesn't make sense. And then on C, they say field forces acts over a distance. That is true. Ne? The other term for field forces is non-contact. Non-contact forces. So they say field forces act over a distance, but they can also act when objects are touching. This is definitely true. Because, for example, think of magnets. Ne? Magnets are going to attract each other from a distance. Even when they come in contact, they'll still hold on until someone comes and separates them. So field forces exist over distances, and even when they're touching, they are still going to exist. Okay, perfect. And then forces always act in pairs of equal strength, but the pairs act on different objects. That is true. Forces act in pairs of equal strengths, but this pairs acts on different objects. So here, basically what they mean is action-reaction pair. For example, if you push a wall, the wall pushes you back with the equal force, but in opposite direction. Does make sense? So it's like you are applying the force on the wall, which is object 1, and then the wall applies a force on you, which is object 2. But those forces that are exerted are going to be of equal magnitude, but in opposite directions. Okay, perfect. So we're done with that. And then let's go to B now. Which one of the following is not a field force? Remember, I said a field force is a non-contact force, right? Gravitational force, we know that is a non-contact force. Electrostatic force is the force between the protons and the electrons. It's the force between positive protons and negative electrons. And they don't have to be touching for it to exist. It can act over a distance. So that is true. And then magnetic force, it's a force between magnets. Magnetic objects do not have to touch for them to experience what? A field force, or for them to experience a force. They can experience a force over a certain distance. And then remember, frictional force is the force that the surface apply on the object to oppose its motion. So here the object must be touching with what? With the surface. The two objects must be in contact for the frictional force to exist. For example, when you're rubbing your hands, the heat that is created in between is because of the frictional force. You cannot feel the frictional force if two objects are not in contact. Perfect. The correct unit of a gravitational force, remember, gravitational force. Ne? The unit of a force is in newtons. The unit of a force is in newtons. Ne? And we use a balance scale to measure a force. We call it a balance scale. Ne? So if they ask you what instrument is used to measure a force, we use a balance scale to measure a force. Ne? Remember, kilogram is mass. Ne? Newton is gravitational force. So the other term for gravitational force is weight. Ne? Don't confuse weight and mass. Those are two different things. Weight is the gravitational force that the Earth or any other planet exerts on objects. But mass is the quantity of matter in an object and is measured in kilograms, and weight is measured in newtons. Okay, perfect. We can move on to the next question. Which one of the following substances is magnetic? Okay. Here are well-known magnetic substances, right? So before I answer this question, let me just write all four well-known magnetic substances. Ne? For magnetic substances. The first one, the most common one, is iron. And then we have nickel. We have cobalt. And then we have neodymium. We have neodymium. Okay. So it's iron, nickel, cobalt, and neodymium. So by looking at these options here, we can see that cobalt will be our option in this case, right? Please learn this for magnetic substances. No? Perfect. The electrostatic force between two charged objects is F. No? Sure. The distance between them is increased. So obviously, this is a field force, right? The more the distance is increased, the weaker the force becomes, because those objects are far away from each other. So the strength of the force decreases. If the objects were brought closer to each other, the strength of the force was going to increase. So they say, how does the distance between them being increased affect the force, obviously the force is going to decrease. So the correct option is B. Right. Perfect. Now let's look at F. An astronaut has a mass of 80 kg on F. Which one of the following regarding mass and weight of the astronauts on the moon is correct? Remember, let's differentiate mass and weight. Mass is the quantity or the amount of matter in an object. So me being Clinton, I have the same amount of matter when I'm on Earth and when I'm on the moon. But I'm going to experience different gravitational force on the moon and on the Earth. On the Earth, I'm going to experience a stronger gravitational force than when I'm on the moon. That is why when we look at those videos of Neil Armstrong and other astronauts who went to the moon, we can see that they are floating, right? They are basically struggling to be in direct contact firmly all the time with the surface of the moon because the force of gravity or the weight, remember I said the force of gravity is the weight. It's very weak in the moon. So now before I go more and more, let's just focus on here and answer the question and move on. The mass will be the same. Yes, I agree. The weight will also be the same. I refuse. So that is out. The mass will be less. That is out. The mass will be the same. And the weight will be less. Yes. On the moon, you are going to experience a lesser force of gravity or a lesser weight than when you are on the Earth's surface. So the correct answer is C in this case. Okay. Perfect. Now let's go and answer number 3. Decide which of the following statements are true or false. If they are false, rewrite them to make them true. Okay. Now let's see the first one. A force cannot make a motionless object move. This is false, obviously. And then when you correct it, you are going to say a force can, you remove cannot, right? Can make a motionless object move, right? Or you can say a force can move a stationary object, right? Provided that the force is greater than the frictional force. Okay, perfect. Now let's see this one. A force can make a moving object change direction. This is very much true, right? And then also a force can change the shape of an object. That is true. For example, if you were to compress a tin can, right? The shape is going to change. The compression is called a force. And that force changes what? The shape of the object, right? Perfect. For example, to change the direction of a force, you can hit a tennis that is approaching you with a bat. It's going to move in an opposite direction. Perfect. Let's check D. A tension force slows down or stops an object because of the surfaces rubbing against each other. This is false, right? This is false. Here you have two options. No? You can say a tension force is a force that is a result of a string, a chain, or a similar object being pulled on both ends. Right. The force that results is a tension force when a string, a rope, a cable, or a similar product, a similar object, it's pulled on both ends of the object. Or you can say, you can replace this. You can say, okay, this is not the tension force. You can say a friction force. A friction force slows down or stops an object because of the surfaces rubbing against each other. That is a frictional force. Okay. Perfect. Let's go to E. Even E, they say lightning is an application of magnetic force. This is false. Lightning is an application of it's electricity, so it's electrostatic force. It's an application of electrostatic force. Okay, perfect. Remember, magnetism works with poles, North Pole, South Pole. but electricity or lightning works with electrons and protons. Okay. On question 4, they say, okay, have a look at the following images. Okay, let's look. We can easily see that this guy here is pushing the table. The arrow tells us that he's pushing. Here he's pulling it. Okay, perfect. So now here, let's see. Which situation shows a push? This shows a push. Which situation shows a pull? This one shows a pull. And then we're done with that question. We get 1 mark. The boy is pulling a desk with a force of 70 Newton. Okay. A frictional force of 20 Newton is experienced. Okay. Draw a free body diagram. Okay. Free body diagram. Okay. In the space below to show these forces acting on the desk. Right. Okay, perfect. So as to draw a free body diagram, what you do is this. Ne? You're basically going to represent your object with a dot. Ne? So a dot always represents an object. Right. And then the pull is pulled. You can see there that it's pulled in that direction. 70 newtons. Since I don't have, okay, I have a rule actually. Let's do this. I'm going to try to rotate my ruler quickly. Okay. So I'll make each centimeter to represent 10 newtons. No? So it's pulled basically how many centimeters? 1, 2. So it's 1, 2, 3, 4, 5, 6, 7, which is 70 newtons. And then the frictional force, it's 1, 2, 3, 4, 5, which is 50 newtons. No? Okay, perfect. And then basically, they must move from the center of the dot, right? So this one, I'll call it pull force. You always name them. This one is a frictional force, right? And then you always show that, okay, here it's 20 Newton, oh, 20, so I need to measure. Okay, guys, we need to measure just 2 centimeters, no? So 20 newtons. And then here it's 70 newtons, right? Now let's talk it. You must know that frictional force always acts in the opposite direction of the object. So if the object is pulled this way, it's going to move that way. Then the frictional force is going to oppose the motion. So it's acting in the opposite direction. So in the opposite direction, we're experiencing 20 newtons. And then this direction, we're experiencing 70 newton. Then there's what we call a net force, né? Which is the second question, basically. A net force is the overall force that the object experiences, né? Is the sum of all the forces experienced by the object. Okay, so what you do here is this. All the forces that are in the direction of the motion, you make them positive. Né? Then we're going to say, okay, the 70 is positive because it's going in the direction. The 20 is a negative because it's going in the opposite direction, right? And then this sum gives us a net force of positive 50 newtons. Do you see? Which is basically, you can say 50 newtons in the direction of motion. When you give a force, you always give the direction. Ne? We call this a vector quantity. So a vector quantity, you always give direction. Okay. If it was, let's say, if your final answer was negative, you're going to say negative 30, and then you say 30 in the opposite direction of motion. Okay. The other term here, they'll say resultant force. Ne? So net force or resultant force is the sum of all forces acting on an object. Okay. Perfect. Let's go to number 5 now. Okay, before I go to number 5, I want to give another example. Let's say we had another object here, and then it's experiencing 10 newtons, and let's say 60 newtons, right? What will be our F net or net force? Our F net, I'm sure you agree that all of them are in the same direction, so our F net will be positive 70 newtons, which is 70 newtons in the direction of motion. Perfect. And then now let's go to question 5. Question 5. Right. Now let's see. A force of 50 Newton and 80 Newton act on a block, okay? Calculate the net force acting on the block if the forces are acting in the same direction. If the forces are acting in the same direction, they're going to have the same sign, so we just add them, right? So it's going to be 50 plus 8, right? Which basically becomes 130 newtons. So the resultant force will be 130 newtons. If the forces are acting in the opposite direction, you're going to have 50 plus 80 equals to 30 newtons. So the resultant force is 30 newtons. No? Perfect. Obviously, it's going to be in the direction of the bigger magnitude. So it's always in the direction of 80. Do we see it? Perfect. Okay. So now let's check the next question. So on this question, they want us to write down 3 different effects that a force can have on an object. Okay, these are pretty simple. We know that a force can change shape, of an object. It can change direction of a moving object. And it can move a stationary object, right? It can move a stationary object. And those are the 3 effects of a force. Okay. Then now we can go to the next question, which is question 8. They say, tabulate the distinctions between mass and weight by making use of definitions of mass and weight and comparing units they are measured in. So here I just made a table for this. Okay. So mass, by definition, I said, is the amount of matter in an object. It remains constant regardless of location. Whether you are on Moon, Mars, wherever you are. On Earth, your mass, your quantity of matter, what you are made up of remains the same, right? Weight is basically another term of gravitational force acting on an object due to its mass. So it's the weight that you are going, weight is the force of gravity that you are experiencing because of your mass. Perfect. And weight is different on different planets. Perfect. Units. Weight is measured in newtons and mass is measured in kilograms. Mass in kgs, weight in newtons. Okay. Symbol. Mass is measured, it's symbolized M in physics, or it's a universal accepted letter in science to represent mass is the M, and for weight is the capital letter W. Influence of gravity, right? Mass is unaffected by gravity. Your mass will be the same. Your amount of atoms, amount of matter that you are made up of remains the same, right? But weight depends on the gravitational pull of the planet or celestial body the object is on. Your weight on Earth is not going to be the same as your weight on Mars, your weight on the Moon. Does make sense? Perfect. And those are basically the differences between weight and mass. They are very important. I'm sure you're going to be asked this in an exam. Don't forget that. Okay. And then now, number 9, they say write down the formula. You need to write down what? The formula. Okay, let me just get my pen first. They say we need to write down the formula that relates weight, which is capital letter W, to the object's mass. Okay, so this is pretty simple. The formula for weight, né? It's mg, right? Explain what each symbol represent. Okay, so on this formula here, we have W, we have small m, we have small g. This is force of gravity, né? Force of gravity measured in newtons. This is your mass in kgs, right? Then this is your gravitation. The g is the gravitational acceleration of a planet. Gravitational acceleration of a planet. Let's see, there's something wrong with my pen. Okay, let's see. Of a planet. Perfect. And then we're done with number 9. Let's go to 10. They say, okay, what 2 factors affect the gravitational force experienced between the object? Explain the relationship. Okay, so weight, remember gravitational force, ladies and gents, we said it's weight, right? So weight, right? It's affected by a capital letter W, sorry. It's affected by 2 factors. No? The first one is the distance between objects, distance between objects, right? And then they say we must explain. The bigger the distance, the weaker the weight. The weaker the weight. And vice versa. By vice versa, I mean the smaller the distance, vice versa. The smaller the distance, the stronger the force will be. The second factor will be mass of objects. Mass of objects. Right. The greater the mass, the bigger the weight. The bigger the weight. And vice versa. By vice versa, I mean the smaller the mass, the smaller the force of gravity will be experienced. Okay, and done with number 10. Let's now go to 11. Let's go to 11. On 11, okay, they say an astronaut performs an experiment to determine the relationship between mass and weight of different planets. He takes a scale and sets off in a spaceship and measures his own weight on different planets in the solar system. The following table indicates his results. Right. They say A, they say we must calculate what? The astronaut's weight on Earth if his mass is 80 kg. Okay. So you need to know the gravitational acceleration for F. The G for F is 9.8 meters per second squared. This is a standard accepted gravitational acceleration for F. Say GE here. And then the G on moon, I also advise you to know it. It's 1.6 meters per second squared. But this one, if they ask you a question, they might give you, but if they don't, it's very safe to no, because they usually like the earth and the moon, né? Because those are examinable. Okay, sure. So they want us to calculate what? The weight. Remember, we have a formula that I gave. We said W equals to mg, right? Then we have our mass. They gave it to be 80 kg. So it's 80. Our gravitational acceleration is 9.8. Let's check how much will that give us. So we have 80 multiplied by 9.8. 9.8. That gives us 784. That gives us 784. Don't forget to say newtons because it's a force. You always give the units. Okay, now let's check C. On which planet is Kevin's weight the smallest? Okay, let's check. You just check here. Remember here it's what? 784. Right. Let's see. 287 Mercury. So the weight is smallest on Mercury. So the answer for C, you'll say Mercury. Mercury. And then they say, what does this tell you about the size of this planet in relation to other planets? Its mass is smallest. Ne? Its mass is smallest. Remember, the smaller the mass, the smaller the force of gravity on that planet. Perfect. Then we're done with this question. Now we're going to check this one. Okay. Question 12. They say we need to draw a what? A diagram that illustrates a magnetic field around a bar magnet. Okay, so a magnetic field around a bar magnet, we'll represent it with a rectangle like this. Perfect. And then we have the two poles. The first pole is the North Pole. Then we have the South Pole. That is our bar magnet. Now let's show the field lines. Ne? So the field lines are like this, basically. Ne? You have this one. You have two. You have three. You have this. Okay, I always just like putting two and then this out, that out, and then this out, and then that out. Ne? Sharp. And you need to know the direction. The field lines always move from the North Pole to the South Pole. Ne? So from the north, the arrows will be going out. Ne? The North Pole to the South. In the South Pole, they are going in. Ne? And if we check here, let's just discuss some few things. You see, closer to the poles, the magnetic field lines are very closer to each other. This represents the strongest magnetic force. Ne? Is the strongest on the poles, right? But as you move outside, you can see that the field lines are a distance apart, which represent that the magnetic force gets weaker outside of the field lines. I mean, outside of the poles. See, even here, they're very close to each other. So that is the representation of a bar magnet, right? It's in red. So the answer for this was just in red. The black color, I was just making additions. Okay, now let's check 13. You do an experiment in class to investigate the bar magnets. You place two magnets next to each other on the table and place a sheet of paper over the magnets and sprinkle iron fillings over the paper. Remember, iron filling, iron is magnetic, as I said above, so it's going to show some movement. You then turn one magnet around and do it again. You see the following patterns. What does photo A and B show us? Okay, let's check them. So what you need to know here is this. Like poles are going to repel each other. They're going to push each other away. So for example, if one magnet North Pole is facing the other magnet's North Pole, you're going to see some repulsion. The field lines are not going to join. They're going to repel each other. Okay, so on A, you can see that they are joining these field lines here, you see? So it's either we have a north pole here and a south pole, or we have a south pole here facing a north pole of that side, right? So basically photo A represents opposite poles of a magnet faced closer to each other, né? Resulting in attractive force. Né? So this is attractive. It represents attraction. Né? Attraction. This represents attraction. And here you can see that these lines are going out like this, and then these ones are not touching, they are going there. These ones are going there. You can therefore conclude that if this is the south pole, that is also the south pole, because same poles are going to push each other away. If this is the north pole, that is also going to be the north pole. And here we have repulsion. No? Repulsion of magnetic poles. Okay, perfect. Now we can go to 14. Let's go to 14. I'm going to bring 14 up. And 14, they say, complete the table by determining the overall charge in each object. Show your calculations and state whether the object is positively charged or negatively charged or neutral, and why. Okay, for 9 marks. Okay, sure. That should be an easy task. You just count how many negatives you have. So you have 4 negatives, so you have -4. How many positives? 1, 2, 3, 4. So you have 4 positives. So the overall charge will be 0. Né? So this will be neutral. Neutral. And then they say why? Because the amount of positive and negative charges are equal. Then we say an object is neutral. Né? Let's count the negatives here. 1, 2, 3, 4, 5, 6. -6. Positives we can see is 3. The overall will have -3. So here we're going to say negative. Your reason will be there is a surplus, or there are more electrons than protons. Remember, the negative charges, we call them, these ones we call them electrons. Né? Electrons. And then the positive charges, we call them, these ones we call them protons. So there are more electrons than protons in this case. Therefore, we say an object is negatively charged. Okay, let's check this one. Check the negatives. 1, 2, 3. So it's -3, positives +7, which becomes 4. +4. So you're going to say this is positively charged, as we have an excess of protons or positive charges. There are more positive charges than negative charges. That is perfect. Now we can move on to the next question. So on the next question, a balloon is rubbed against a jersey and the balloon picks up a negative charge. Okay, so here we need to assume that before we rub these objects, right, we are having neutral objects basically. So the amount of protons and electrons are equal in both. Ne? Sure. And then because the balloon gains electrons, it means it is having an electron affinity that is higher than of the what? The J's. Ne? Electron affinity is basically the ability of an object to gain electrons. So it steals electrons from another object. Ne? Sure. Now, they say explain where these negative charges come from. Ne? Make reference to both protons and electrons in your answer. Okay. For this one, to save time, I'm not going to write. I'm just going to explain. Right? Perfect. When we rub the balloon and the jersey, right? There is a frictional force between the two objects, right? The frictional force causes an electron transfer between the two objects, right? Because the balloon has a higher electron affinity. Electron affinity is the ability of an object to attract what? Electrons from the other object. Since the balloon has a higher electron affinity, it's going to steal or to take electrons from the J's, resulting in an excess of electrons. And then hence we're going to say it is negatively charged, right? And the Jz, we will say it is positively charged, right? And that's the answer. But I just want to elaborate more, right? So you need to know that the only charge that is able to move is basically what? Is the electron, because it's found in the outer orbitals of an atom. The protons cannot move. If you remember when you draw the Bohr model in grade 8, the protons used to be inside the nucleus. They are locked. They are locked inside the nucleus. Ne? So to break the nucleus, you need the strongest force ever. Ne? So protons will never move. Only electrons are the ones that move. So the protons of an object will always remain the same before and after run, but electrons will change. The other one will gain, the other one will lose. And if the other one gains 2, it means the other one lost 2. So in this case, the balloon gained, it means the Jz lost. So the Jz is no longer neutral, the balloon is no longer neutral. The balloon is negatively charged because it is having more electrons now. The Jz is positively charged because it is having more protons now, so it's positively charged, right? Name the type of force that the balloon and the Jz will experience during rubbing. Remember, I said this is the frictional force, right? This is friction. Name the type of force that the balloon and the Jz will experience after rubbing. Now it's going to be electrostatic force. Electrostatic force. Will the force in C be referred to as attractive or repulsive? It's going to be attractive because the two objects are now oppositely charged. The other one is negative, the other one is positive. So oppositely charged objects experience attractive forces of electrostatic. So just like opposite poles, opposite charges also attract. Same charges are going to repel each other. Okay, sure. Then let's check question 16. On question 16, what do you think these two girls are touching on the left of the photo? They are touching what we call a Van der Graaf generator. Van der Graaf generator. Perfect. So we answered that. Explain your answer and what is happening to them. So guys, a Van der Graaf generator is a generator that when put on, there are going to be a buildup of charges on the surface of the generator, right? Either negative or positive, right? And then as the girl touches the generator, the charges are transferred from, remember this is no longer, remember the girls are neutral before they charge, but the generator was not, was not neutral. So the charges are going to be transferred from the generator to the girls, right? And the reason why their hair is raising is because the buildup of charges goes to the hair, and those charges, remember, they are of the same sign. So they're causing repulsive forces on the strands or at the end, on the hair, causing it to lift up and in opposite direction. You see, the hair strands are repelling each other because of the same charge that is being transferred. It's causing repulsion. And then that's it, right? Question 17. Here we're just going to discuss. They say, write a short paragraph to explain how lightning is formed. Okay, so lightning is formed in this way. On a very hot day, we know that water is going to evaporate, right? And as it evaporates, it carries with it dust particles and other dirty materials up, right? And as it goes up, remember the hot water is going to cool down and form what we call condensation. So it is going to condense. Né? And the condensed water vapor is what you see as the cloud. Né? The reason why the cloud that is associated with thunderstorms is very dark is because of the dust particles caused by evaporation, right? So those dust particles and ice particles are going to form frictional force, né? Which causes the transfer of electrons and protons. The electrons are usually heavier. The electrons are heavier than protons. So you're going to find electrons like this, basically. Okay, let me just draw a typical cloud, thunderstorm cloud, right? So you're going to have this, basically. You are going to have this. Let's say this is your cloud, right? Your cloud, your cloud, your cloud. Electrons are heavier than protons, so electrons are going to be here. Né? They are going to go to the bottom because they are heavier than positive charges. Né? And then protons are going to go up. Né? They are going to float up like that, right? Sure. And then as this process of friction continues, né? There is a buildup of charges. So the charges keeps on increasing, right? And then this excess of electrons is going to go down now. Né? And then remember here, as it comes down, it's going to meet with tall buildings and trees and all that. And then these particles, basically, they are going to, if there's positive charges there on top of the buildings, they are going to attract these negative charges here. Né? And this will form lightning, right? Also inside the cloud, as the charges builds up, these positives and negatives are going to attract, forming a lightning, right? And that is how lightning forms. Perfect. Then they say, why is it wrong with the following scene? Explain your answer. Okay, it is wrong because sitting under the tree or any tall, closer to any tall building outside, it's very dangerous because lightning conducts itself through those tall buildings and trees to reach the ground, right? So a tree is more prone to being hit by a lightning. So any object, any animal, anything closer to a tree will also highly likely be struck by a lightning, causing fatalities when the lightning strikes the tree. So that is why this is wrong here, right? You can't play outside like this, closer to the tree, if there is a lightning. Né? And you know, precautionary measures to take. You have to avoid touching metal objects, stay indoors, avoid standing on windows, and all that general knowledge. And that's it about forces. The video that will follow after this will be on electricity. Tango, aluta continua.